Let's run a quick thought experiment. Imagine we somehow traveled out into deep space, scooped up a single tablespoon of a neutron star, and gently placed it right here on the surface of the Earth. If you know a bit of astrophysics, you probably know the classic trivia answer. Because a neutron star is incredibly dense, that tiny spoonful of matter would weigh over 1 billion tons. That is roughly the mass of Mount Everest, sitting right there on a piece of silverware. Beyond the sheer weight lies a more immediate threat. The second that spoon arrives, it detonates. This explosion is large enough to instantly vaporize a massive chunk of our planet. To understand why, you have to look at the forces holding that star together. In space, the immense gravity of the star compresses its material, holding it in a delicate balance against something called neutron degeneracy pressure, a force that naturally wants to push all that matter apart. When you take a spoonful away from the star, you leave the gravity behind. The pressure instantly wins, and the matter violently expands. This extreme thought experiment reveals a very basic rule of physics. Whenever matter is suddenly stripped of the environmental pressure holding it together, it expands, quickly and often violently. You don't have to go to a dead star to experience this. You just have to buy a plane ticket, because the exact same physical law governing that stellar explosion is what makes ascending into the upper atmosphere one of the most mechanically hostile environments the human body can endure. We rarely think about it, but humans are bottom dwellers living deep inside an ocean of gas. Down here at sea level, the weight of the entire atmosphere stacks up above us, pressing against every square inch of our bodies with almost 15 pounds of continuous force. Our biology expects that exact amount of pressure to function normally. But as an aircraft climbs past 10 or 20,000 feet, that protective blanket of air thins out, and the surrounding pressure rapidly drops. This animated diagram shows Boyle's law. When environmental pressure decreases, the volume of trapped gas proportionally expands. Apply that geometry to your anatomy. You have trapped gas in your middle ear, sinuses, and gastrointestinal tract. As outside pressure drops, this gas physically swells. Usually, this just means your ears pop as the expanding gas slowly escapes. But in a setting pressure drop, like an aircraft losing a window at cruising altitude, the expansion is instant. If you happen to be holding your breath during a rapid decompression event, the trapped air in your lungs expands so fast it can physically tear your lung tissue apart. We rely on the heavy weight of the atmosphere to keep our internal volume stable. Remove that weight, and the gases inside us become an immediate mechanical hazard. If we climb even higher, above 18,000 feet, the pressure drop triggers a breakdown in our blood chemistry. This animation illustrates Henry's law, which dictates how dropping pressure affects dissolved gases. Think of a sealed can of soda. The carbon dioxide stays suspended while under pressure. The second you drop the pressure, the gas comes out of solution and forms bubbles. Every breath you take on Earth is 80% nitrogen, which dissolves directly into your blood and fat tissues. When atmospheric pressure falls away at altitude, you become the opened soda can. The stored nitrogen escapes, bubbling directly out of your physical tissues. This causes altitude decompression sickness. If nitrogen bubbles lodge in your joints, you get an agonizing pain known as the bends. If they hit your central nervous system, you experience severe neurological disturbances. And if they form in your lungs, you suffer a dangerous, suffocating condition called the chokes. When the cabin pressure blows out, the resulting vacuum immediately compromises your ability to breathe at a chemical level. At 40,000 feet, atmospheric pressure is so low that the normal inward flow of oxygen stops entirely. This shows reverse diffusion. The extreme low pressure reaches into your bloodstream, pulling oxygen out of your blood, forcing it back into your lungs. Your body is actively drained of the oxygen it already has. In this environment, an average person's time of useful consciousness plummets to as little as 9 seconds. The extreme cold and thin air of the upper atmosphere are dangerous, certainly, but it is the sheer lack of physical pressure that actively strips the oxygen from your cells. Humans survive high-altitude flight by using engineering to bring the ground-level environment with them. Commercial aircraft use isobaric pressurization systems, engine compressors constantly pump ambient air into the cabin faster than outflow valves let it escape. This creates an artificial, highly pressurized bubble that keeps the environment inside feeling like a comfortable 8,000-foot elevation, even when the plane is flying near the stratosphere. Before these systems were perfected, researchers and flight surgeons relied on altitude chambers, sealed steel drums attached to heavy vacuum pumps, to safely expose early aviators to the brutal physical realities of low pressure. Those early tests proved exactly what happens when the artificial bubble pops. It's why modern high-altitude aircraft require specialized backup systems. Pressure-demand oxygen masks physically force oxygen into the lungs using positive pressure, counteracting the vacuum outside. It is also why military crews and astronauts often sit for half an hour breathing 100% oxygen before a flight. This nitrogen washout routine flushes the dissolved gas from their blood, removing the very particles that cause the bends before they ever leave the tarmac. Whether it's a spoonful of ultra-dense matter stripped from a dead star, or a human pilot climbing toward the edge of space, the physical rule remains absolute. We are entirely defined by the forces pressing down on us. We are, at our core, creatures built for the heavy bottom of an atmospheric ocean. And stepping outside that invisible, life-giving weight requires every ounce of our engineering ingenuity to keep ourselves from tearing apart.